Hello. Today we're going to wrap up chapter 6 and we're going back to all three states of matter. So the last couple of lectures we were really focusing on gases and how we can calculate things like pressure, volume, temperature, or amount of a gas. Now today we're going to talk about changes in state. So what happens when we go from a solid to a liquid to a gas? Or what if we go backwards? So changes in state are often accomplished by adding or removing heat from a substance. So, for instance, maybe you're boiling water to make some tea, or you're boiling water to make pasta. When you're boiling your water, you can probably tell that it's coming off as steam. So the water itself is going from a liquid to a gas because we're putting in heat. The opposite of that, let's say we have our hot tea that's sitting out and we forget about it, which I often do, and then an hour later, it's ice cold. So during that process, we're losing heat. And maybe if it's cold enough, the water turns to ice. So changes in state caused by adding heat to a substance are classified as endothermic. And changes in state caused by removing heat are classified as exothermic. So endothermic means that heat is coming in. So we would say that that's a positive value because heat is coming in. And then an exothermic process involves the release of heat. So we would say that that is negative. The system is losing heat. So down below we have endothermic versus exothermic processes. So, for instance, in order for a solid to turn into a gas, we need to provide heat. And it is possible for a solid to turn directly into a gas. So, for instance, if you've ever used dry ice before, dry ice is made of carbon dioxide, and it starts out as a solid and then goes directly into the gas phase. So dry ice is actually used at parties sometimes to kind of create a smoky effect. There was actually recently a tragic event where I believe in Russia, somebody put dry ice into a pool and they didn't have proper ventilation in the room, and many of the people at the party experienced carbon dioxide poisoning because they were inhaling the gas. So that process of a solid turning into a gas is called sublimation. All right, hopefully I didn't bring the mood down too much with that last example. So another endothermic process, if we go from a solid to a liquid, we also need to add heat to the system, so it's endothermic. And when a solid turns into a liquid, that process is called melting or fusion. And then if a liquid turns into a gas, that also involves an absorption of heat. And we call that process evaporation or vaporization. Now on the right-hand side, we have some exothermic processes or changes in state. So let's say that a gas is turning into a solid. We would call that deposition or condensation. And when a gas turns into a solid, it's actually releasing heat into the environment. And then if a liquid turns into a solid, we call that freezing or crystallization. And that also involves a release of heat. So the liquid is cooling down to turn into a solid. Now, if a gas turns into a liquid, we call that liquefaction or condensation. And that also involves a release of heat into the environment. All right, so just a little more detail and some nice figures here. Again, for the endothermic processes, evaporation or vaporization is an endothermic process in which a liquid is changed to a gas. So off on the right, you can see a picture of a warm lake or body of water that's releasing some steam or vapor there. And then sublimation is an endothermic process in which a solid is changed to a gas without first melting to a liquid. And so on the right-hand side is a picture of some dry ice or solid CO2. And then melting or fusion is an endothermic process in which a solid is changed to a liquid. So for instance, melting ice. And then for exothermic processes, liquefaction or condensation is an exothermic process in which a gas is changed to a liquid. So for instance, if you've ever woken up in the morning and seen some condensation on your windows, that is, of course, the process of condensation. So any moisture in the air is depositing itself onto the window, and it's cooling down enough to become a liquid. Now, I have a lot of condensation on my windows during the winter, and I have a feeling I should probably ask someone about that. All right, so deposition is an exothermic process in which a gas is changed into a solid. So here we're skipping the liquid phase again, but in the opposite direction. So for instance, if it's cold enough outside, moisture in the air can, in its gaseous form, can just solidify very quickly. And you can see some ice crystals forming here. And then freezing or crystallization is an exothermic process in which a liquid is changed into a solid. So if you've ever seen ice forming around branches on a tree, that of course is freezing or crystallization. All right, so how do we put all of this information together? So we're going to use the example of what's called a heating curve to demonstrate all of these different processes. So down below we have a heating curve for water. So on the y-axis we have increasing temperature, and on the x-axis we're adding heat. And you'll notice that the unit for heat here is calories. So heat is related to energy, and one of the units for energy is the calorie. All right, so let's say we're starting with a 1 gram sample of ice at negative 20 degrees Celsius. And then we're going to convert that to steam at 120 degrees Celsius. So this is actually a 5-step process. So down here, we're going to start at negative 20 degrees Celsius, and our 1 gram sample of ice is going to start to heat up as we're adding energy. And from A to B, we have a solid that is being heated up to what's called a melting point. So that melting point is 0 degrees Celsius for water. Now, the melting point will be different for different substances, but this is for water in particular. Now, once we hit that point of 0 degrees Celsius, the ice is actually going to start melting. So at that point, we'll have a mixture of solid and liquid. Now, you'll notice that that line is flat compared to the previous line from A to B, which was increasing. So during the process of melting, any heat that's being added to the melting ice is going towards that melting process, and it's no longer going towards the increase in temperature that we saw from before. So, So a flat line equals no change in temperature. Now, you've already done a lab where you saw this heating curve for water, and you might have been asked a couple questions to kind of get you thinking about that process. So now we're actually kind of deep diving into all of those different processes. All right, so after we reach the melting point, then we have all liquid. So now we're going to add more heat, and the liquid is going to heat up to water's boiling point, which is 100 degrees Celsius. All right, and then once we hit the boiling point, then the liquid is going to start turning into steam. And again, we have a flat line, so we don't have an increase in temperature. Instead, all of the heat being added to the liquid is going towards the boiling of the liquid. And then after we've boiled off all of the liquid, so all of the liquid is turned to gas, then we also have an increase in temperature for the gas. So what I'll do is add a couple of labels here. So down at the bottom, we start with a solid, and then as it's in its melting point from B to C, we have solid plus liquid. And then after the melting point, we just have liquid. And then during the boiling process, we have liquid and steam or gas. And then after everything is boiled, then we just have gas. Okay, so there are a couple of other things we need to talk about in terms of this heating curve. So vapor pressure is the pressure exerted by a vapor that is in equilibrium with its liquid. So for instance, let's say we have a liquid in a container that's closed, and it starts to evaporate. So maybe we're heating it up. So after some time has passed, more of the liquid will turn into gas. But remember, this is a closed system, so the gas can't escape, right? So at some point, we're going to reach something called equilibrium. At that point, the rate of evaporation is going to equal the rate of condensation. So what's really interesting is that as these gas molecules start to form and build up, they're going to hit each other. So maybe these two hit each other, and that can cause them to cool down and sink back into its liquid state. So we have these two competing forces. We have evaporation and condensation. So if we go back to the last figure, so we said that at the boiling point, the liquid is turning into a gas, But we could also go in the opposite direction. So what if we cool a gas? Then we're condensing the gas into a liquid form. So when the rate of evaporation equals the rate of condensation, then we're at equilibrium. So the amount of gas won't change and the amount of liquid won't change. We just kind of stay at that constant amount of liquid and gas. Now, the boiling point of a liquid is the temperature at which the vapor pressure of the liquid is equal to the atmospheric pressure. All right, so for instance, let's say you're boiling a pot of water for pasta or tea or whatever, and you put a lid on top. Eventually, the vapor that builds up on top of the water or above the water is going to reach what's called the, it's going to reach atmospheric pressure. And that's when the water will start to boil. Now remember, atmospheric pressure is 1 atmosphere, or 760 torr, or we could also write 760 millimeters of mercury. So the normal or standard boiling point is the temperature at which the vapor pressure of a liquid is equal to 1 atmosphere. So again, we're boiling water and we put a lid on top. And once we have enough gas molecules that the pressure reaches 1 atmosphere, that's when the water starts to boil. So off on the right, we have a graph showing vapor pressure versus temperature. And water is shown in blue. So, the vapor pressure is going to increase with increasing temperature until we hit the point at which the vapor pressure is equal to 760 torr, or 1 atmosphere. And that's when water will start to boil. So this normal boiling point is different for different liquids. So for instance, ethyl alcohol or ethanol boils at a lower temperature. And that's because the vapor pressure of ethanol is going to build up more quickly than that for water. And part of the reason for that is ethanol evaporates much more easily than water does. So it forms more vapor as we increase the temperature compared to water. So we'll reach the boiling point a lot faster. All right, now all of that being said, the boiling point of water can change based on elevation. So for instance, if you've ever been to Denver, which is the mile-high city, or if you've ever gone to, one of the nearby mountains and, tried to cook or boil water at a higher elevation, you probably noticed that the boiling point, or maybe you noticed that the boiling point of water is a lot less than at sea level. So here in Tacoma, for instance, we're at about sea level, so water boils at 100 degrees Celsius. But in Denver, water boils at 95 degrees Celsius. So why is that? It has to do with the pressure of the atmosphere. So the higher up you go in elevation, the lower the pressure of the atmosphere. So as elevation increases, pressure of the atmosphere decreases, So boiling point decreases. Because remember, in order for a liquid to boil, it just has to reach the same pressure as the atmosphere around it. So in this case, in Denver, that's going to happen a lot more quickly. But additionally, you also have to adjust your cooking times for food at higher elevations. So in cookbooks, sometimes you'll notice it'll state, at this elevation, cook for 20 minutes longer, etc. So a lot of things are affected at different elevations. Now, let's say you go to Mount Everest and you climb up to the top of Mount Everest. Everest is 20,000 feet above sea level. So the pressure of the atmosphere at that height is even lower than in Denver, obviously. It's very, very high up. So the amount of oxygen is a lot less, the amount of nitrogen is a lot less in the air, so the overall pressure is a lot less. So the boiling point will also decrease, and it's actually 76.5 degrees Celsius on the top of Mount Everest. Okay, so let's talk about one more thing, and then we'll do a few example calculations here. So the last concept we'll talk about in relation to changes of state is specific heat. So the specific heat of a substance is the amount of heat required to raise the temperature of exactly 1 gram of a substance exactly 1 degree Celsius. So for instance, when we melt ice, or if we're heating up ice, we need a certain amount of heat in order to increase the temperature of the ice. And actually down at the bottom of this chart on the right here, you can see that we have water as a solid, so that's ice, and it needs 2.1 joules per gram per degree Celsius in order to increase its temperature by 1 degree. And then liquid water needs much more energy in order to increase its temperature. And then steam doesn't need quite as much heat in order to increase its temperature. All right, now let's look at some of the other molecules here. So at the top we have aluminum, which is a metal, and copper, which is also a metal. And you'll notice that the amount of heat or energy that these metals need in order to increase their temperatures are quite small. And then if we go down the chart, we also have, for instance, mercury, which is a liquid metal. It's the only liquid metal at room temperature. And its specific heat is quite small as well. So metals heat up a lot faster than other substances, which is why they're really great for cookware, for instance. They can withstand a lot of heat as well. But then water, for instance, takes forever to heat up. If you've ever watched your water heat up to boiling, it takes a long time, and that's because it requires a lot of heat. So if a specific heat for a substance is large, that means the amount of energy required to heat up that substance is quite large. But if the specific heat of a substance is small, then the amount of energy needed to heat that substance is also small. So metals, again, heat quickly, but that also means that they release heat very quickly. So they don't retain heat. Whereas water heats slowly, But water can also hold on to heat as well. So it retains heat. So water is actually used in nuclear power plants to cool down the reactors, because in nuclear power plants, the reactors are so hot, they're giving off so much energy, and water can absorb that heat and hold on to it. And water is constantly moving through that system so that they can direct heat away from the reactors so that they don't get too overheated. So water is great for that sort of application. All right, so let's finally work on some practice problems. So let's say that a chemist has 2.5 grams of aluminum and 2.5 grams of copper. How much energy is needed to raise the temperature of both metals 1 degree? And which metal will heat up faster? Okay, so on the last slide, we saw that aluminum's specific heat value is 1 joule per gram per degree, and copper's is 0.39. So let's write those down. So the specific heat for aluminum is 1 joule per gram degree Celsius. We'll say degree Celsius there. And then for copper, its specific heat is 0.39 joules per gram degree Celsius. All right, so we have 2.5 grams of aluminum. So we can use the specific heat as a conversion factor to figure out, okay, how much energy do we need? Okay, so we're just going to multiply 2.5 grams of aluminum by its specific heat, which is 1 joule per gram degree Celsius, and we end up with 2.5 joules per degree Celsius. So grams will cancel. And that tells us that for every degree Celsius of an increase in temperature, we need 2.5 joules of energy, for aluminum at least. But let's do the same thing for copper. So we have again 2.5 grams of copper, but copper's specific heat is a lot smaller. So when we multiply 2.5 by 0.39, we end up with, let's see, where did my notes go? 0.975 joules per degree Celsius. So what this tells us is that if we're trying to raise the temperature of both aluminum and copper by 1 degree Celsius, we need a lot more energy for aluminum. We need 2.5 joules for every degree Celsius, whereas for copper, we need a lot less of this energy. So we only need 0.975 joules per degree Celsius. So because we need a lot less energy for copper, copper should heat up much more quickly. So we can compare specific heat values for different substances to see what will heat up more quickly, what will heat up more slowly. And then remember, we also said that that tells us whether the object or substance can retain heat. So this is a pretty useful value. All right, now a couple more concepts here that I'm going to throw at you. Heat of fusion and heat of vaporization. So we just talked about specific heat, which told us the amount of energy we need for every gram of a substance to increase it by 1 degree Celsius in temperature. The heat of fusion, however, is the amount of heat or energy required to melt exactly 1 gram of a solid substance, but heat of fusion occurs at constant temperature, so we don't have a change in temperature here. So for instance, let's say that we're melting ice. So the heat of fusion is equal to 334 joules for every gram of ice. So if we wanted to melt 1 gram of ice, we would need 334 joules of energy or heat in order to do that. So that's another useful conversion factor we can use. And then the heat of vaporization of a substance is the amount of heat required to vaporize exactly 1 gram of a liquid. And again, this is at constant temperature, so temperature won't change for this. So for water, the heat of vaporization is equal to 2,260 joules per gram. Oh, and let me write water here so we remember what we're actually referring to. So what this tells us is if we have 1 gram of liquid water, we will need 2,260 joules of energy or heat in order to increase the temperature just 1 degree Celsius. At a constant temperature. Getting my values mixed up here. Okay, so this is a lot of energy that we need in order to vaporize that 1 gram of liquid. All right, so let's use that heat of fusion that we just went over in an example problem. So a scientist has 500 grams of ice. How much energy is needed to melt that sample of ice? All right, so remember when we melt something, that's also referred to as fusion. And we just said that the heat of fusion for water is equal to 334 joules per gram. So we're going to use that as our conversion factor. Okay, so let's start with the amount of ice, which is 500 grams. And then we're just going to multiply that by the heat of fusion. Okay, so grams cancel, so we'll end up with joules, which is what we want. We want energy here. And 500 times 334 gives us 167,000 joules. Okay, that's a lot. So it might be easier to express this value in terms of kilojoules. So let's convert this to kilojoules. All right, so if we're converting to kilojoules, how many joules are in 1 kilojoule? All right, so hopefully you remembered that it's 1,000. All right, so this will give us 167 kilojoules. That's a lot of energy that we need in order to melt that sample of ice. Okay. So now let's apply everything we just talked about to our heating curve. Okay, so there are 3 different heat equations we can use in order to determine how much heat is needed to, for instance, melt ice, turn it into a liquid, and then boil that liquid. So the first equation we can use tells us that heat is equal to the mass of the substance times the specific heat of the substance times the change in temperature of the substance. So this particular equation can be applied to the first part of our chart where we're heating up ice. And then also the second part where we're heating up a liquid. And then this third part where we're heating up a gas. So anywhere you see a temperature change, you can apply that first equation. Now, the second equation we can use tells us that heat is equal to mass times the heat of fusion. So the only area that we can use that is between B and C. So during the melting step or fusion step, we can use equation 2 to calculate how much heat we need. And then the last one, it tells us that heat is equal to mass times the heat of vaporization. And the only place we can use that is for this step between D and E where we're boiling water. So for the steps where there's an increase in temperature, we will need to look up the specific heat values for the different phases. Because remember, when we saw the water example earlier in our table, there were different values for ice, liquid water, and steam. So we would have to look up those specific heat values. Okay, so I know that's a lot. Let's actually put it all together into an example. So let's say a scientist has 1 gram of ice at -4 degrees Celsius. How much energy will it take to melt the ice at 0 degrees Celsius and then boil the liquid at 100 degrees Celsius? Okay, so what we're looking at here, and let me just clear some space. Oh, need a bigger eraser. There we go. So we're told that we're starting at around -4 degrees Celsius. So our ice is at -4 degrees Celsius. And we're asked, okay, how much energy is needed to melt the ice? So that means we first have to increase the temperature of the ice to 0 degrees Celsius and then melt the ice. And then we were also asked to boil the liquid water, and how much energy does that take? So we also need to increase the temperature of the liquid to the boiling point and then boil the liquid. So this tells us we have 4 different steps. So in the first step, we're heating the ice. In the second step, we're melting the ice. In the third step, we're heating the liquid. And in the last step, we're boiling the liquid. Okay, so for the first step, we'll need equation 1. So step 1, we'll use equation 1. And then we also need the specific heat of ice for that step. And then in step 2, we're going to use equation 2 and the heat of fusion. And then in step 3, we're heating the liquid, so we're going to use equation 1 again, because we have a change in temperature. But this time we need the specific heat of the liquid. And then in the last step, step 4, we're going to use the third equation, equation 3. And this time we'll use the heat of vaporization. And again, this is all for water. Okay, so let's start with step 1. So we're going to use equation 1, heat is equal to mass times the specific heat of ice times the change in temperature, which I'm going to write as delta T. So delta is the triangle, and that just means change. All right, now one more thing, delta T is going to equal the final temperature minus the initial temperature. So we need to be a little careful about that. Otherwise, we'll end up with a negative value, which we do not want. Okay, so from earlier, let's go back a ways and let's look up the specific heat of ice. So at the bottom of the chart, we can see that solid water has a specific heat of 2.1 joules per gram degrees Celsius. Okay, great. So let's go back and we'll plug that in. All right, so we have 1 gram of ice, and then the specific heat of ice is 2.1 joules per gram degrees Celsius. And then the change in temperature is T final minus T initial. So the final temperature here is going to be the melting point. So that's 0 degrees Celsius. And the initial temperature, we were told, is -4. So we're going to subtract -4 degrees Celsius. So that's actually going to give us a value of +4 degrees Celsius. Okay, so 1 times 2.1 times 4 will give us a value of 9.6 joules. Okay, so that's our amount of heat needed for step 1. All right, and then step 2, we're going to use that second equation we saw where heat is equal to mass times the heat of fusion. All right, so we have 1 gram of water, and earlier we saw that the heat of fusion for water is 334 joules per gram. So that's super easy. We're just multiplying 1 by 334. So for step 2, we need 334 joules of energy or heat in order to melt that 1 gram of ice. Okay, so now step 3, we're going back to equation 1. So heat is equal to mass times the specific heat of liquid water. So this is a little bit different. Oh, my pen was freaking out. And then we also need the change in temperature for that step. Okay, so let's go back and look up the specific heat of liquid water. All right, so liquid water is second to last on our table, and its specific heat value is 4.18 joules per gram degrees Celsius. Okay, now let's also look up the temperature difference. So I'm going to go to this chart. So the boiling point of water is 100 degrees Celsius, and the melting point is 0 degrees. So our temperature difference will be 100. Okay, so let's plug those values in. So we have 1 gram of ice. The specific heat is 4.18 joules per gram degrees Celsius. And then the change in temperature is 100 degrees Celsius, so our final temperature, minus 0 degrees Celsius, our initial temperature. Okay, so that difference is just 100, so that makes it easy. So 1 times 4.18 times 100 is 418 joules. Okay. So that's how much energy it takes to heat a liquid or heat liquid water from 0 degrees to 100 degrees. All right, now step 4. For this step, we're boiling the water, so we're going to use that third equation we saw, where heat is equal to mass times the heat of vaporization. All right, so the mass again is 1 gram, and the heat of vaporization for water we saw earlier is 2,260 joules per gram. My pen, don't die on me. Okay, there we go. So this is super easy. It's going to take 2,260 joules of energy or heat to boil this amount of water. All right, so now the last step, we just have to add up all of those different amounts of heat, and that will give us the total energy needed for all of these steps. Okay, so let's add together 9.6 joules plus 334 joules plus 418 joules plus 2,260 joules. Now remember, when we're adding numbers together, we care about the least number of decimal places. So in this case, most of our numbers end in the ones position. So right here, except for one of our values which ends in the tenths place. So what we'll do is we'll round our final value to the ones place. Because remember, we can't be more accurate than our least accurate measurement. So when we add all of these values together, we get 3,022 joules. That is quite a bit of energy when we put it all together. So again, remember, this is the amount of energy we need in order to increase the temperature of the ice to its melting point, and then melt it, and then increase the temperature of the liquid to the boiling point, and then boil it. So that's our heating curve there. Okay, so that's all I have for you for Chapter 6. If you have any questions, please let me know. You can always set up an office hour with me. Next week, we'll start Chapter 7, and I will see you there.